Algebra 2, Lesson 15, Solving Systems of Equations by Graphing. So there is a limitation on what I can actually do on this particular format, so we'll be able to see a little bit more whenever we start answering some questions. Okay, up to this point it's going to be talking about things we can't necessarily see. All right, so systems of equations. That is a collection of two or more equations that contain two or more of the same variables. So it doesn't matter if it's a and b or x and y, but both equations have to have the same variable. So if one has x, y, the other one has to have an x and a y. A and b, p and q, that type of thing. All right, a linear system contains two linear equations in two like unknowns, meaning that a linear system, it has to be two linear equations. You can't have like a quadratic and a linear, right? It's a linear system has to have two linear equations, really at least two, okay? We can solve systems of linear equations with even more than that, but linear systems can be solved by graphing. Both of the equations are graphed on the same coordinate grid. The coordinates of the point where the lines intersect or cross give the solution. So if they give me two linear equations and they say solve, right, what they're talking about is where do these two lines intersect at. The intersection is the solution. So our solution should be a coordinate pair. Okay, does that make sense? All right, so just knowing what kind of answer we're looking for is sometimes helpful. If they give me a system of linear equations, so like, you know, y equals 4x minus 2 and y equals 7x plus 3. We're looking for where they cross. Where do they meet? Where do they come to the, what do they have in common, right? All right. All right, so not all solutions to a linear system will intersect at integral values of x and y, meaning that they don't, by integral, right, or an integer, not everything intersects at a nice neat number like 4, 2 or 0, 0 or 1, 3 or something, something real definite, you know, where I'm going to see, you know, my little grid lines cross and it crosses right at that point. Sometimes they'll cross at decimal points, right? They'll cross at fractions. Sometimes where they cross is really far away. It's off of our normal little 10 by 10 grid, right? Okay, so a graphing calculator enables more exact solutions to be found. We can find those fraction coordinates. Does that make sense? All right, solutions of systems are still ordered pairs. There are three possibilities for the number of solutions to a linear system. One ordered pair, an infinite number of ordered pairs, or no ordered pairs. Let me be specific. Let me explain this here for a second. If we're saying that there's one ordered pair, that means that the lines intersect at exactly one spot. Okay? These are lines that have different slopes. Okay? They have different slopes. They may or may not have a different y-intercept, but they have different slopes. Okay? Let's see. An infinite number of ordered pairs means that whenever I simplify these two linear systems, I see that they're actually the same line. Okay? That's what we mean by their intersection is an infinite number because they cross everywhere. They are the same thing. Okay? Does that make sense? Okay? And then we have no ordered pairs, which means these two lines never intersect. In order for that to happen, these two lines, when simplified, have the same slope but different y-intercepts. Okay? So one ordered pair is a combination of different slope, maybe yes, maybe no on the y-intercept. Infinite number of ordered pairs is exact same slope, exact same y-intercept. No ordered pairs means same slope, different y-intercept. Okay, does that help? All right, and then they start to classify these with some terms that you may not be super familiar with, and you're going to need to know these, and you're going to need to know these situations. Okay, so a linear system that has at least one solution is called a consistent system. Okay, notice that it says at least one solution. Okay, that means that we can use, I believe, a consistent system for either one ordered pair or infinite number of ordered pairs. Okay? So consistent we'll use for an intersection or all intersections is consistent. Okay? No solution is an inconsistent system. No solution means the lines are parallel. Okay? So parallel lines are always inconsistent. Everything else is consistent. Okay? All right. Then we have dependent and independent. All right? A linear system is dependent when one of the equations in the system contains all solutions common to the other equation in the system. Essentially, what you should see is this is overlapping, okay? Overlap, where it's the same line. It's going to be a dependent system. What happens to one will be the exact same thing that happens to the other because they're the exact same line. Okay, does that make sense? All right. All right, so we can see from this that two lines that overlap is going to be a consistent dependent system, right? All right. All right. Otherwise, the system is independent, meaning that if I'm crossing one time, it's going to be a consistent independent system. Okay. And let's see, no ordered pairs is going to be an inconsistent independent system. Okay, I think I've got all that right. We do have a chart to make sure that I'm not wrong. Okay, and it looks like this. Okay, classifying systems of equations. Okay, lines intersect at one point, one solution. System is consistent and independent. Okay, so it's a nice little chart to keep because for tests and homework, they're going to say classify this system of equations. What they're meaning is it consistent or inconsistent? Is it dependent or independent? So this simple chart will help you nail it down every time. Okay? All right, lines coincide, meaning they're the same line, infinite number of solutions or ordered pairs. It's consistent and it's dependent. Lines are parallel, no points in common. System is inconsistent and independent. So if I said something wrong earlier, see the chart. Okay? Always go with the chart. Okay, you've got the chart in your book and you've got it in your Chromebook now. All right, so that's everything that they give you here. Let's look at some questions. Okay. There's multiple ways that we could choose to solve this by graphing. For instance, the way that this is set up, I don't know if we've talked, because sometimes I overlap between Algebra 1, Algebra 2, Algebra 3, and geometry. One of the ways that we can solve this, rather than just going through all the steps to convert it to a slope-intercept form, have we talked about x and y intercepts in here? Yes? Okay, Eric's giving me a heads up. Yes? Okay, that means that if I want to know on this equation where it's going to cross the x-axis at, right, I'm going to plug in 0 for y and solve for x, correct? So I'd plug in 0 for that. I'd get negative 5x equals 6. I'd divide by negative 5. I'd get negative 6/5 as a decimal. Let's see. Negative 6 divided by 5 comes out to like negative 1.2 is where it's going to cross the x-axis. All right, that looks kind of like that spot right there, does it not? All right, let's look at where it would cross the y-axis at. We'd plug in 0 for x. We'd get 4y equals 6. Divide by 4. 6 divided by 4. Okay, just as a fraction is 1.5. So we can see right there, correct? Okay, if we were just going to graph that line. Does that make sense? Okay, so we could see how we could use x and y intercepts to graph. But let's see if we can figure out how we can find a solution to these two equations. Anybody know how we might find a solution? All right, well, this is probably getting into some stuff that's going to take place in later lessons, but to find a solution, one of the things that we can do is we can eliminate one of these variables. Okay, for instance, I could multiply this whole equation by 4, right? If I've got negative 5x plus 4y equals 6, and I multiply all of this by 4, that's going to give me 12x minus 4y equals 8. What am I doing here, Eric? Right, because whenever I add these two equations together, I can cancel out those y's. Negative 5 plus 12 is 7x. and 6 and 8 is 14, which means the x-coordinate where these cross is what? 2. Okay, again, we should probably see, we can see that, okay? Now what I would do is to get the y-coordinate where they cross, because I don't actually know this yet, okay, is plug in my x, right? So I'm going to just plug it into that equation there. 3 times 2 minus y equals 2. 6 minus y equals 2. Subtract 6. I get negative y equals negative 4. Y equals 4, right? Okay, so what I get is that spot right there is going to tell me where the solution is. Okay, does that make sense? Okay. All right, so there are multiple ways to end up solving those. We can plug them in. In order to plug it in my graphing calculator to get that answer, I would have to change both equations over to y-intercept form. Do we know how to do that? Okay. Move everything over to the other side and solve for y on both of them. Okay. All right. Kind of come down here a little bit. These say solve by graphing, so they really do want you to just to draw the line and see where they cross at. Again, we can do that by our x and y intercepts. We can do that through, in this case, what's really kind of nice about this is that if I subtract these two equations, right, what's going to happen with my y's? Will my y's cancel out if I subtract the two equations? Yeah, meaning I don't always have to add them. But what I do have to remember is that I'm subtracting. All right, so my y, because 4y minus 4y cancels out, here I have to be careful because this is 3x minus negative 2x. Do I have two negatives there? Yes. So it's going to end up being 5x. And I've got negative 36 plus 16, which should be what? Negative, no. Negative 36 minus negative 16. So that's negative 36 plus 16. Negative 20. All right, so x is going to be negative 4, right? Okay, now I can plug that back in, right? Let's go up to, let's try 3 times negative 4 plus 4y equals negative 36. Negative 12 plus 4y equals negative 36. 4y equals, we're going to add it, so I should get negative 24. Divide by 4. Y equals negative 6. Am I going too fast for anybody? No. So my coordinates for where I'm going to get here are negative 4, negative 6. Okay, that's what I'm looking for. Do I find that anywhere? Yeah, I get that down there. Okay, so that's how I can find a solution without graphing. Would we all understand how to solve by graphing? Do we all know how to graph these lines? Okay, this next one, I'm not going to go straight to the solution. We're actually going to graph it. If they give me another one. And here, let's do number 8. All right, let's convert this over to slope-intercept form. I've got negative 2x plus 5y equals negative 15. I want to convert that to slope-intercept form. What's my first thing? Add 2x. So I got 5y equals 2x minus 15. Okay. Divide by 5. So y equals 2/5 x minus 3. Okay? Now, let's do the other one. We got negative 12x plus 10y equals 10. Okay? Add 12x. 10y equals 12x plus 10. Divide by 10. Okay, so y equals, no, not 2x, 6/5. 6/5 x plus 1. Okay, so let's go about this. All right, with my first one, what's the first thing I want to do with that? Okay, beginning point is 3. 1, 2, 1, 2, 3, 4, 5. 1, 2, 1, 2, 3, 4, 5, something like that, right? And I could go down 2, right? 1, 2, 1, 2, 3, 4. Okay, something like that. Down 2. Probably is going to take me all the way over to here, right? Okay, can make me a nice, neat little line there. Okay, now let's do our other one. Up 1. Up 6. 1, 2, 3, 4, 5. Well, we go up to 7. Okay. Okay, down 6, so that'd be down to -5. All right, so we found our spot right there, didn't we? What is that coordinate location? Looks like, no, look. -5, -5. Okay, that's how you solve by graphing. Okay, but so for today, these are going to come out. They probably are mostly going to be at nice, neat little, coordinate locations. Okay, but they won't always be. Okay. All right. I want to make sure that I give you guys some time to get started. That way I can answer some questions. Do we feel like we've got a pretty good handle on this point? Still kind of a review for us. Okay. Now, some of the other questions that are in here, though, that we didn't cover, all right, are identifying the system, state, is this consistent, dependent? So we're going to need to probably solve that. We're going to need to be able to see. And the easiest way to check that is to put it in the slope-intercept form. All right? Same thing with number 4. Some of these are a little different if you have questions. Right? Those are good questions to look at some point, are 5 and 6 and 7. We didn't do any of those. So there's several more questions we could have looked at.